have previously seen the Shewhart chart, and we have seen the QSIM chart. And the Shewhart chart just looks at one observation or one subgroup at a time. And the QSIM takes into account the entire history, all equally. Maybe it would be useful to put a greater emphasis on the recent history rather than looking at the entire history and treating it all as equally important. The EWMA, exponentially weighted at moving average, does just that. The score is defined as follows. We have a mixture of the current value WT here and the previous score. And the parameter alpha, which has to be between 0 and 1, regulates how much emphasis we put on the current score as current value as opposed to the previous score. And just to initialize, we set W0 to mu. What does this formula mean? We can expand it by plugging it in and then recursively expand it. So we get the score is equal to alpha times the current value, alpha times 1 minus alpha times the previous value, plus alpha 1 minus alpha squared times the value before that, and so forth. These coefficients are getting smaller and smaller because alpha is between 0 and 1. Now, if we have a large alpha value, we are really mostly looking at the current value and the recent past. If we have a very small alpha value, we are reaching farther back into the distant past. This formula is meant to give insight. We don't use it for calculation because this has more terms, right? The previous formula just had 2 terms, much easier to calculate. So here's an example in form of a question for you. Assuming alpha equals 0.2 and setting W0 to mu. And here's our formula. What is the EWMA value at time 1? And so this is the same data as before. I will leave you to answer this, and you can convince yourself that some of the other values are correct also. All right. So we can show for large T that if the process is in control, that the expectation is mu. And we can show that the variance is approximately this variance. That leads to a 3 sigma control limits, plus minus 3 times sigma, and then the square root of this term. The only thing is that we can't interpret the 3 sigma control limit as in the Shewhart chart, where we said, well, that leads to 2.7 errors out of 1,000 observations. That doesn't work like that here, right? Okay. So the recommended value of alpha, if you don't know anything else and you just have to start somewhere, is 0.1. But of course, you can tune the process and get a different value for alpha for any one particular application. Looking at the data in our example with the mean shift after 20 observations, and the mean shift was just very subtle, just 0.2 standard deviations. So we apply the control limits, and as we can see, absolutely nothing happens. We do not detect the shift in the mean. That was with alpha equals 0.2. If I use alpha equals 0.1, we detect it near the end here at 180 observations. And if we choose an even smaller value, I went to 0.03 here. I'm not sure why exactly 0.03, but just a smaller value, then we discover it earlier. And remember that small values for alpha have the ability to incorporate more of the distant past. And since the shift we're trying to detect is very, very small, it's 0.2 sigma, smaller values work better here. All right, this is the end of this segment.